The screen share is not visible properly. Yes, it is visible now.
ଭଲ ଅଛି ଚଲ
পাঠিয়ে দিয়েছি।
হ্যাঁ দেখে নিচ্ছি।
ঠিক ঠিক।
So, am I audible properly?
Yes, yes.
Okay. So we'll start.
Can I start now?
Okay, let us start. Okay, start. Respected dignitaries and dear participants, myself, Dr. Rajesh Kumar Agrawal, HOD of Physics Department. I, on behalf of the organizing committee, short-term training program 2025, heartily welcome to all the participants. The topic of this short-term training program is recent trends in sustainable development. I feel very much honored to welcome our resource person or speaker of this session, Dr. Sukhdev Sahu, Associate Professor of Department of Physics, National Institute of Technology, Durgapur. First of all, let me give a brief introduction of Dr. Sahu. Dr. Sukhdev Sahu has completed his MSc and MPhil from Utkal University, Bhubaneswar, and PhD from NIT Durgapur. His research area is theoretical high energy physics, boson phenomenology, and CP violation. He has 22 years of long teaching experience and 25 years of long research experience. He has 90 research papers to his credit in international and national journals. He has guided 15 PhD scholars and completed 6 different projects by Government of India and other statutory bodies. He has received Young Physicist Award for 2011 by Odisha Physical Society and Albus Nebus Marquess Lifetime Achievement Award. Today, Dr. Sahu will deliver a talk on recent advances in high energy physics. Now I am inviting Dr. Sahu to deliver his speech. And Dr. Sahu, please take over the session and start your lecture.
Thank you. First, I thank the organizers to invite me to deliver a lecture in this STP. My special thank to Dr. Rajesh Kumar Agrawal who invited me for this program. Today I will deliver a talk on recent advances in high energy physics. Plan of my talk, fundamental forces and their unification. Since the most of the audiences are the students, I have planned my talk starting from the fundamental or basic things, starting from that fundamental forces and their unification, then standard model of particle physics and its drawbacks, then Higgs boson, which is popularly known as God particle, then existence of massive neutrino, and after that I will give a brief conclusion of my talk. Fundamental forces of nature. I think our students who are present in this seminar, they know about fundamental force. They have read already from their high school about the fundamental forces. So what do we mean by a fundamental force? So fundamental force is a force by which particles interact with each other and which cannot be explained in terms of other forces. Like fundamental particles. Fundamental particles are those particles whose internal structure cannot be explained in terms of other particles. But the other particles can be explained in terms of these particles. Similarly, these are the fundamental forces which cannot be explained in terms of other forces. In the nature, there are 4 different types of fundamental forces: the gravitational force, weak force, electromagnetic force, and strong force. The gravitational force, I think all of us know that any two material particles, this gravitational force exists. If you consider, basically, this gravitational force is responsible for the gravity by which we stand on the surface. At a larger scale, this gravitational force is responsible to bind the planets in the solar system. to our sun. And further, if we consider about the galaxy, the stars in the galaxies and galaxies in the universe, we know that in our universe, there are around 10 to the power 11 number of galaxies, and every galaxy contains around 10 to the power 11 number of stars like our sun. So we can say that roughly in our universe, there are 10 to the power 22 number of stars like sun. So how large is our universe? But this large structure of the universe is due to this gravitational force. Then comes to electromagnetic force. This electromagnetic force basically exists between any two charged particles. For example, our electrons, which are negatively charged particles, they are moving around the nucleus, around the which is positively charged due to this electromagnetic force. This then comes to weak nuclear force. This weak force acts in the atomic scale. For example, if we consider the case of a neutron, which present inside the nucleus, it decays into proton, an electron, and an anti-neutrino, electron type neutron. This is known as beta decay. So this is one example of the weak force. Similarly comes to the strong force. This strong force basically exists between the quarks, which consist of these protons, and the protons and neutrons, which are the constituents of the atoms. Now we will discuss about these fundamental forces. The carrier particle for this gravitational force is graviton. Similarly, for electromagnetic force, photon. For weak force, W plus W minus Z0. And for strong force, gluon is the carrier particle or mediator particle. The mass of these carrier particles for gluon 0, photon 0, graviton 0, and W plus W minus Z0, their masses are 80.4 and 91.2 GeV. Generally, in particle physics or in high energy physics, we are using one type of units. We are acquainted with that SI or CGS system. But in particle physics, we are using another unit which is known as natural units, where this mass is expressed in terms of a GeV or electron volt. And from their range, you will see that this electromagnetic force as well as gravitational force, they are long-range forces, whereas strong force and weak forces are short-range forces. If you will compare their strength, and if you will consider the strength of a strong force as 1, then electromagnetic force is 10 to the power minus 2, weak force 10 to the power minus 12, whereas gravitational force is 10 to the power minus 39. So from this table, we can say that strong force is the strongest among all fundamental forces, and gravitational force is the weakest among all the fundamental forces. But this weakest force or this gravitational force is responsible for the large structure of the universe. From the Big Bang model of the universe, actually, till now we do not know how our universe is created. The origin and evolution of the universe is not known clearly so far. But there are many theories which are proposed to explain the origin and evolution of the universe. One of them is the Big Bang model, which is the most successful theory to explain the model of the universe so far. And from this Big Bang model of the universe, we know that at the time of a Big Bang, when the universe was created, all the fundamental forces were unified. If you see this figure, you will see that at the time of a Big Bang, all the four forces were unified. Then as time passes on, at 10 to the power minus 43 seconds, 10 to the power minus 43 seconds after the Big Bang, this gravitational force separates from this unification. So from that time, we are getting two forces. One is that gravitational force, and another one is that unification of a strong electromagnetic and weak forces. Similarly, as time passes on, at 10 to the power minus 35 seconds after the Big Bang, from this unification, a strong force separates. So from that time, we are getting three forces. One is that gravitational force, strong force, then electroweak force. Again, at 10 to the power minus 11 second after the Big Bang, the splitting of electroweak force occurs. So from that time, we are getting 4 fundamental forces. That means at 10 to the power minus 11 second from the Big Bang, we are getting 4 fundamental forces in the universe. So since at the time of a Big Bang, all the 4 forces were unified, that is why nowadays the scientists, they are trying to unify all the fundamental forces to study about the origin of the universe. What was the universe at the time of a Big Bang when it was created? Then comes to standard model. Physicists are trying to unify all the fundamental forces of the nature with a view to develop a fundamental theory. But till today, the scientists or physicists are able to unify only 3 fundamental forces out of these 4, except the gravitational force. They are able to unify. They are able to unify means actually they are writing some mathematical equations in which we can express. From that mathematical equation, we can explain these 3 fundamental forces except gravity. The standard model of particle physics expresses our present understanding of known fundamental fermions. These are quarks and leptons, and the forces between them, that is the electromagnetic force, weak force, and strong force. This model is also known as quark-lepton model because this model contains 3 generations of quarks, that is 6 quarks, and 3 generations of leptons, that are the 6 leptons. What are these 6 quarks and 6 leptons? You will see that in this table, these are the electron type neutrino. These are muon type neutrino, tau type neutron. These are 6 leptons. Whereas these up quark, down, charm, strange, top and bottom. So these are 6 quarks and 6 leptons, which constitute the standard model. That is why our standard model is also known as the quark-lepton model. And these quarks have some unusual characteristics. Before the discovery of a quark, basically what we are expressing the charge of any particle, that was in terms of the charge of electron, integral multiple of the charge of 1 electron, 1e, 2e, like this. But after the discovery of a quark, it is found that the quarks have some fractional electric charge. How much that charge? In this table also it is present. Here you will see that the up quark, charm quark and top quark, they have the charge of 2/3, whereas down, strange and bottom quark, they have -1/3 charges. Electric charge. These are the electric charges. Again also, these quarks have another type of charge, which is known as color charge. These quarks are of 3 colors. One is that red, blue, and green. These are the first generation quarks and leptons, second generation quarks and leptons, third generation quarks and leptons. And it is found that these first generation quarks and leptons are found in ordinary matter, whereas second and third generation quarks and leptons are found only in cosmic rays and accelerators. With increasing, one of the properties that with increasing the number of generation, the particles become heavier. For example, if you consider the case of a top quarks, the top quark which is discovered at the end, we can say at last, the mass of a top quark is maximum among all the quarks. So it is the heaviest quark. Now, these leptons can propagate freely, whereas quarks are confined in hadrons. They can only exist in bound states of 3 quarks, which are known as baryons. For example, proton consisting of that UUD, 2 U quarks and 1 D quark. If you see that the charge of U quark, 2/3. So 2/3 plus 2/3 minus 1/3. So that is the charge of a proton. Similarly, neutron consisting of a UDD. The charge of U up quark is 2/3, then 2 down quarks, -1/3 minus 1/3, that is 0. So in case of a neutron, the charge of neutron is 0. Similarly, those of a quark and antiquark. These are known as mesons. So mesons contains one quark, one antiquark. Till today, we can say that to date, almost all experimental tests of three forces are described by the standard model of particle physics. That means what we are observing in the experiment, from the experiment, it is predicted theoretically. That means the experimental results satisfied with the theoretical predictions. Almost all, not all. These are the standard model elementary particles. These are the quarks, up, down, charm, strange, top, bottom, lepton, electron type neutrino, muon type neutrino, tau type neutrino, and these are the carrier particles. Gluons for strong force, photon for electromagnetic force, W and Z for weak forces. And you will see that here the Higgs boson is present. It has given a special status or special position, the Higgs boson, in the periodic table of elementary particles in the standard model, because it has some unique properties. That is why it has given a special status. I will explain about this Higgs boson little more when I will discuss about Higgs boson separately. This Higgs boson is the last particle of a standard model which has confirmed at the LHC on 14th March 2013 in that Mariana conference, Italy. What are the limitations of this standard? Already I said that till date, this standard model of predictions agrees with experimental results, but there are some results which are not satisfying the standard model predictions. Those are known as recently it is called as anomalies. Those anomalies I will explain if I will get some time. Then the limitations of the standard model, already I have said that in the standard model, we have unified these three fundamental forces except gravitational force. So this standard model does not incorporate gravity. Without gravity, this standard model is incomplete. This is why the string theory comes into picture. Standard model may be called as theory open. Actually, from the Big Bang model, we know that at the time of a Big Bang, all the fundamental forces were unified. That is why the physicists are trying to unify all the fundamental forces, but they are able to succeed only to unify 3 out of 4. So if there exists a theory which would be able to unify all the fundamental forces, then that theory will be called as theory of everything, TOE. So if TOE exists, then this standard model will be called as 3/4 of everything. In this article, that physics, which is published in 2005 in Physics Education, which is a popular article. In that article, I have given the title of a standard model, alternative title for standard model as 3/4 of everything. Then why I have given as 3/4 of everything? Because it unifies. The standard model unifies 3 out of 4 fundamental forces. So if TOE exists, then standard model will be called as 3/4 of everything. Similarly, about string theory, actually there are many theories proposed nowadays, which with the help of which we are trying to unify all the fundamental forces. But one of these theory is string theory. Actually, it is a theoretical attempt or proposed theory, which we can say that is able to unify all the fundamental forces. How? This string theory is actually, nowadays, actually, when the string theory was originated, it was 26-dimensional. Then after discovery of supersymmetry, this string theory's dimension is reduced. How? If you consider a 2-dimensional rod, if you increase its length to infinity, then we can say that width will be negligible. We can neglect that one. So it will behave as a 1-dimensional object. That process is known as compactification. So in the string theory, with the help of this compactification, the dimension, 6 dimensions, we are trying to compact 6 dimensions. Then that means in the string theory, there are 6 extra dimensions. We are acquainted with 4 dimensions, x, y, z, t, but there are 6 extra dimensions. So this string theory is one of the proposed theory which would be called as a theory of everything. But so far, it is not conclusively discovered, because this string theory, if you go to the previous table, where I have shown that mediator particles, that gluons, photons, W plus, W minus, these are spin 1 particles. But this graviton is a spin 2 particle. But the mathematical structure, the mathematical equation which is required to explain the spin 1 particles is different from that of the spin 2 particles. That is why in one mathematical equation it is possible that structure is actually SU3 cross SU2 cross E1, that our students who are present here, they may not be able to understand. That is why I am not going to discuss here complicated mathematical equations. But this graviton, which is a spin 2 particle, so with that mathematical structure, it is not possible to explain graviton. That is why this unification is not, there is some problem to unify this gravitational force with the other forces. Another point is that string, the size of a string is of the order of 10 to the power minus 33 centimeter, which is known as Planck length. But the particle accelerator, detector, whatever may be available, the powerful instrument in our universe so far, it is possible to detect the size of 10 to the power minus 17 centimeter. So if the intensity or power of that accelerator or detector will be 10 to the power 16 times more, then it is possible to detect this string theory at the experimental or laboratory. That is why Stephen Hawking said it is not possible to detect this string in the laboratory till 2050. It is not. His prediction said that within 2050 it is not possible to detect this string in the laboratory. That is why you will see that there is another popular article which is published in European Journal of Physics in 2009, where I have written a popular article about string theory, whose alternate name I have given as string theory big problem for small size. So due to extremely smallness of this string, it is not possible to detect this string in the laboratory. That is why this theory is not completed so far. Similarly, there is no explanation why there are 3 generations. I said first generation, second generation, third generation, not 2 generations or 4th generations like that one. It is also not explained in the standard model. Similarly, it cannot explain about the existence of a dark matter and a dark energy in the universe. In the universe, whatever may be the powerful instrument we are using, that a telescope or microscope or detector, accelerator, etc., with the help of these powerful instruments, we are able to visible only 5% of the universe, but 95% we are not able to see. That is known as the darker side of the universe. Out of these 95%, the dark matter is 27%, whereas dark energy is 68%. So these 95% of the universe are not visible till today by the scientists. Similarly, the standard model cannot explain the matter-antimatter asymmetry. According to the Big Bang model, when the universe was created, at that time there were equal amount of matter and antimatter. But nowadays, in the present universe, we are able to see there are more matter than that of the antimatter. This is known as matter-antimatter asymmetry or baryon asymmetry. So this matter-antimatter asymmetry is not explained in the standard model. It does not explain the existence of a massive neutrino. Already I said that there are 3 different types of a neutrino. One is that electron type neutrino, muon type neutrino, and tau type neutrino. These 3 neutrinos are massless in the standard model of particle physics. But very recently, we can say that, but it is found that it has some mass. However tiny may be, these neutrinos are massive, and these massive neutrinos exist, or it is possible. Sorry. And from that neutrino oscillation experiment, it is found that these neutrinos have some mass, however tiny it may be. So these massive neutrino, the existence of a massive neutrino is not explained in the standard model. So these are some limitations of the standard model, or these are some phenomena which are not explained with the help of a standard model. Nowadays, what I said, that the physicists or scientists, they are able to unify the fundamental forces. For example, Maxwell unified the electricity with magnetism, taking optics as integral part and constructed electromagnetism. Then the quantum theory of this electromagnetism was constructed by Feynman, Swinger, and Tomonova, which is known as quantum electrodynamics. So this quantum electrodynamics is the first relativistic quantum field theory. This quantum electrodynamics is the first relativistic quantum field theory, which explains the interaction of light and matter. Then this quantum theory of electromagnetism is unified with weak interaction by Abdus Salam, Steven Weinberg, and Glasgow, and they constructed the electroweak theory. In analogous to that of quantum electrodynamics, physicists also constructed the quantum theory of strong interaction. The theory of a quark interaction, this strong interaction is the quark interaction, was constructed in analogous to that of the quantum electrodynamics, which is known as quantum chromodynamics. Then, by symmetry of, by combining this, so this quantum theory of a strong interaction, which is known as quantum chromodynamics. So in quantum chromodynamics, strong interaction is there. In electroweak theory, electromagnetic force and weak force is there. So now this, when this symmetry of electroweak theory and the color interaction combine, they gives the grand unified theory. But you will see that in this grand unified theory, this is the strong force and this is the electromagnetic force and weak force. So three forces are there. The simplest grand unified theory is the standard model. But in this grand unified theory or standard model, our gravity is not present. So when this gravitational force will be unified with this grand unified theory, then that theory will be called as quantum gravity. But so far, this quantum gravity is not constructed completely. One of the proposed theories is string theory. Other theories are Kaluza-Klein theory, etc. And six-dimensional theories are there. But so far, the most successful theory is the string theory. Then comes to Higgs boson, which is popularly known as God particle because it is providing mass to all particles we are thinking of. So Higgs boson is a particle which is responsible for the mechanism which is known as Higgs mechanism, by which all particles acquire mass. It is theoretically predicted by England, Brout, Higgs. Actually, first two authors, that England and Brout, these two scientists, they published one paper. And Peter Higgs, the third one, he published another paper. Then another three scientists, that Guralini, Hagen, and Kimmel, these three scientists, they published one paper. So these three papers are published in 1964 in internationally reputed journal, that is the Physical Review Letters conjugatively, in the same year. But date of publication is very important because I will show that in which date they have published and who has got the Nobel Prize for this Higgs boson. Why the date of publication is very important in this case. So the standard model suggests that just after the Big Bang, all particles were massless. As time passed, the universe cooled and temperature fell below a critical value, and invisible field called the Higgs field filled all this space. Now, this one of the property of Higgs field is that it is exactly same everywhere, whereas magnetic or that gravitational force varies from place to place. Even if space were to be emptied completely, it would still be filled by the Higgs field. We do not notice it. Higgs field is like air to us or like water to fish. Now, when particles are moving in a uniform Higgs field, they change their velocity. That means they accelerate. So this accelerate means change of velocity, and this Higgs field exerts a certain amount of resistance or drag. This is the origin of inertial mass. Why do we are saying about the mass of any particle? Generally, while we are saying about the mass of a particle, generally we are considering about inertial mass. So this inertial mass is due to that interaction of the particle with the Higgs field, basically. So Higgs boson gives mass to all fundamental particles. These fundamental particles constitute this all matter present in the universe. If Higgs field was not there or Higgs boson was not there, then we are not able to exist here. If Higgs field suddenly disappear, then what will happen? All matter would collapse as the suddenly massless electron disappear at the speed of light. So we know that only that massless particle can move with the speed of light. So if Higgs boson was not there, Higgs field was not there, then we would be massless and all of us should move with the speed of light. So the speciality of Higgs field is that it breaks the symmetry of nature. When the universe was created, there was no mass, no particle. So now this symmetry of nature was broken by the Higgs field, and it gives masses to the particles. The particle which is associated with this Higgs field is known as Higgs boson. In the standard model, there is only single Higgs particle, but in the minimal supersymmetric extension of a standard model, there are 5 Higgs boson: 2 CP even neutral Higgs boson, 1 CP odd neutral Higgs boson, and 2 charged Higgs boson. There are 5 different types of Higgs boson, but in the standard model, there is only 1 Higgs boson. What is the properties of the Higgs boson? Actually, the matter particles have a spin half, and gauge particles are spin 1, but the Higgs boson has a spin 0. At present, there are no known elementary particle whose scalar boson in nature. It is only 1, and it does not mediate the gauge interactions. And Higgs particle interacts with the other particles and gives masses to them. If the interaction is more, stronger the interaction, stronger is the mass of the particle. The Higgs boson does not couple to photons and gluons. That is why these photons and gluons are massless. So far in the universe, we are saying that only these photons and gluons are massless particles. So far we know. Higgs boson has, that means we can say that Higgs boson provides mass to all particles. That is why when the Higgs boson was discovered, popularly it was called as Higgs God particle, but the Peter Higgs, who was the discoverer of this Higgs boson, was not satisfied with that name. But popularly we are calling it as God particle because it is, we know that God is omnipotent and it is present everywhere. It provides power to everyone. Similarly, here God particle is also, this particle is providing mass to all particles, including itself. On 14th July 2012, this at the LHS experiment, they announced a new elementary boson known as Higgs-like particle, and on 14th March 2013, this new result were presented in that conference, Mariana conference at Italy, and these data confirm the discovery of Higgs boson, and its mass is around 125 GeV. We can say there are actually at the Large Hadron Collider, there are 6 detectors are there. One of the is Atlas and another is CMS. These 2 particles are dedicated basically to study the B mesons and Higgs boson, CP violation, etc. And they measured the mass of Higgs boson around 125.5 or 25.7, around we can say that 125 GeV. And we, that means I and my supervisor, Professor L. Lakshmindra Maharana and Professor A.K. Maikop, we have also predicted the mass of a Higgs boson in 2006. The Higgs boson was discovered in 2012, but in 2006, 6 years before, we have also predicted the mass of Higgs boson theoretically around 120 GeV. So our result was 4% less than that of the experimental value. Maybe while we are calculating this mass of the particles, we have considered some parameters. Maybe we have left some parameter, which that is why we are getting 4% less. And there are some anomalies exist regarding this particle because already we have said that there are 5 different types of Higgs boson in the minimal supersymmetry standard model, but in the standard model only one particle. So the Higgs boson which was discovered experimentally at the laboratory, whether this particle is the standard model Higgs boson or beyond the standard model, till now it is not confirmed. But although its properties are not well measured, the data accumulated so far consistent with the standard model predictions. That means the data which are measured in the laboratory, it is found that they are satisfying that standard model predictions. That is why we are thinking that it may be that the standard model Higgs boson. If the new boson is the standard model Higgs boson, then all its properties are predicted once its mass is known. Although the Higgs boson belongs to the standard model of particle physics, its study is very challenging and fascinating topic, which interplay between different branches of physics like particle physics, condensed matter physics, and cosmology. How it is related with this condensed matter physics and cosmology, I will give you one example here. In the condensed matter physics, not recently, in 2004, one material was discovered, which is known as graphene, which is a two-dimensional nanomaterial. So this nanomaterial, two-dimensional nanomaterial graphene, actually when we compress graphene, it ripples and displays some sort of symmetry breaking. Again, we know that our Higgs boson is related with that of the symmetry breaking. That is why the physicists, they are thinking that there is some relation between this graphene and Higgs boson. That means this Higgs boson is related with this condensed matter physics, the branch of a condensed matter physics. The ripple effect of a graphene would give hints about the Higgs field and Higgs boson. Similarly comes to another branch of physics, that is the cosmology. Basically in the cosmology, we have studied about that dark matter. What is that dark matter? I am not going in detail, but this dark matter is basically in 1933, when the scientists studied about the different galaxies. Actually, it is found that the mass of the stars present in the galaxy is less than that. What should be the mass of that universe, or we can say that total galaxy? It is less than that of the observed mass. That is why the observed mass is less than the actual mass. So that means we are unable to detect some masses which are present in the universe already. So that mass is known as dark matter, basically. And this dark matter, there is some property of this dark matter is like that. It is responsible for the discrepancy between the apparent observed mass of the universe and its actual mass. Again, this dark matter does not interact with electromagnetic force. Similarly, this Higgs field does not interact or couple to photons. That is why it does not give to mass to the photons. So here, dark matter does not couple to that of the photons, we can say, or electromagnetic force. Similarly, here Higgs boson does not couple to photons. And another point, Higgs boson gives masses, and this dark matter is explaining the unseen mass of the universe. That is why these are the similarity between this dark matter and Higgs boson. That is why the physicists, they have thought that there is some relation between this dark matter and this Higgs boson. In 1912, one theoretical physicist, Hertzberg, he predicted the mass of a Higgs boson around 125.7 GeV from this dark matter distribution of the universe. So there is a relation. Although this Higgs boson belongs to the particle physics, is a particle of belongs to the standard model of particle physics, but it has some relation with different branches of physics like condensed matter physics and cosmology. In 2013, on 14th March, this particle was confirmed that it has a zero spin and positive parity. So it is very likely that of the standard model Higgs boson. And it is the first elementary scalar particle in 2013 Nobel laureate, that Englert, that I will discuss elaborately for what purpose or for which work they have got the Nobel Prize, that I will explain a little bit matter. And they have predicted that the discovery of dark matter or dark energy will crown the Nobel Prize in future. Then 2013 Nobel Prize in Physics for the discovery of a Higgs boson. Basically that already I said that 6 scientists, physicists, that Englert, Braut, and second paper was published by single author Peter Higgs, and third paper was published by another 3 authors. So they published that first 2 authors, that England and Braut, published their paper in 31st August 1964. Then second paper 19th October, and third paper 16th November 1964. They detected as in that paper, they were the first to give the idea about the field that interacted with the fundamental particles and gave to them mass. Higgs was Peter Higgs, that was the first to point out the potential existence of a Higgs boson, and he said this Higgs boson is basically responsible for providing the masses to fundamental particles, and these fundamental particles constitute the entire universe. Then these 3 scientists, they describe more compressive exposure of the mechanism, which is known as actually Higgs, England, Braut, Goralnik, Hagelkabel, these 6 scientist mechanism. Now commonly it is known as Higgs mechanism. So it is the product of several particles. You will see that out of these 6 scientists, you will see that this Braut was expired in 2011. So before the declaration of Nobel Prize for 2013, this scientist expired. So they have announced the Nobel Prize for this Englert and Higgs. So these 2 scientists received the Nobel Prize for 2013, but they did not include the names of other authors who have the equal footing or contribution for this mechanism, because there is some restriction about the Nobel Prize that maximum 3, it can be given to maximum 3 people. But here one, that Englert, and another one Peter Higgs, so they did not consider about these authors. Although in another paper, these 6 scientists have received that 2010 American Physical Society Sakura Prize, because another paper that Stephen Weinberg, another Nobel laureate, he cited them all equal footing on his landmark paper, a model of leptons. So these 2 scientists, basically the first 2 papers, 2 authors, scientists, they received the Nobel Prize for 2013 for their theoretical discovery of a mechanism that contributes to our understanding of origin of mass of subatomic particles, and which was confirmed through the discovery of a predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. This is the contribution of 6 scientists for this Higgs mechanism, and they received that J.J. Sakurai Prize for Theoretical Particle Physics in 2011. Then comes to another particle, massive neutron. Already I said that in the standard model, these neutrinos are massless, but later on it is found that these neutrino has some mass, and this mass, the existence of a massive neutrino is not explained with the help of a standard model. For studying this massive neutrino, we are studying beyond standard model. Actually, I and my group is working in the beyond standard model. We are studying about this Higgs boson and also some B-meson decays, where we are studying about the phenomena related to beyond standard model. So discovery of a neutrino oscillation. What is that neutrino oscillation? Actually, already I have said there are 3 types of a neutrino. One is that electron type neutrino, muon type neutrino, and a tau type neutrino. These are 3 flavors, neutrino flavors. But it is found that these neutrinos change or transform their flavor. That means neutrino transform from one form to another form. This phenomenon is known as neutrino oscillation. And for the neutrino oscillation, the mass of a neutrino should be present. That means in order to exist this neutrino oscillation, neutrino must have a mass. It is claimed. And for the discovery of a neutrino oscillation, these two scientists, Professor Kajita and Professor McDonald, they have received the Nobel Prize in 2015. And this Professor Kajita was the leader of Super Cameo kind of collaboration, whereas that is Sudbury Neutrino Observatory, that ISNO director was McDonald. They received the Nobel Prize for the discovery of neutrino oscillation, and which shows that neutrino have mass. What neutrino, basically where it is present, these are the neutrino sources. From Big Bang we are getting these neutrinos. Then from sun, that the fusion, that solar neutrino, and similarly supernova neutrino, and atmospheric neutrino. I will a little bit explain about this, what is that atmospheric neutrino and what is solar neutrino. Then for this neutrino, actually, these Nobel Prize received for the neutrino related Nobel Prize in 1988 for the discovery of a muon neutrino, 1995 for the detection of a neutrino, in 2002 detection of a cosmic neutrino, and 2015 for the discovery of a neutrino oscillation, which shows neutrino have mass. Actually, what I will explain here, I will say about what was their experiment, but I am not expert about their experiment, how they have done, how they have got their result, but what they have got their results, I will explain here. Then I will express my view, theoretical explanation, why neutrino must have mass. What is that solar and atmospheric neutrino problem actually? That in 1960, John Bach, he was trying to study what types of neutrino processes are occurring in solar fusion. I think our students who are present in this seminar, they know about this solar fusion. That in the sun, hydrogen plus hydrogen, helium, and so on, like iron, the stable, and neutrino, basically, they are produced here. Our aim is to study about the solar neutrino. Basically, it is predicted that solar neutrino, around 100 billion solar neutrino are passing through our body every second. But they interact so weakly with other matter that remarkably little is known about them. That is why it is very difficult to detect this neutrino. The fusion reactions that takes place in the sun only produce electron type neutrino. So in order to detect these neutrino, this Bahakal teamed up with Ray Davis and performed the experiment that Homestake gold mine in South Dakota. What they detected about the solar electron neutrino, actually they detected this solar electron neutrino flux at Earth, which is about 1/3 of the theoretical value. What was theoretically prediction about that in electron neutrino, but experimentally when it is detected at the Earth, it is found that its value is 1/3 of the theoretical detection. It is known as solar neutrino puzzle. Similarly, in the atmosphere, these neutrinos are created as a consequence of a cosmic ray protons from space hitting Earth's atmosphere. Basically, Earth's atmosphere contains protons and neutrons. When this cosmic ray, which consisting of a proton, collides with the proton and neutron of the Earth, that means proton-proton collision and proton-neutron collision, they produce charged pions. Here you will see that these pions, and these pions decay into muons. These muon and the muon type neutrino. Again, this muon decays into electron and muon type neutrino and one electron type. So as a result, here we have got two neutrino, muon type neutrino and one electron type neutrino. That means for two muon type neutrino, we are getting one electron type neutron. That means the ratio should be nu mu by nu e should be 2. It is theoretically, but experimentally, when it is detected, it is found that for every electron neutron there should be. This is atmosphere theoretical prediction. For every electron neutron, there should be 2 muon neutron. But in that experiment, they observed that the ratio is 1. This is atmospheric neutrino puzzle. But these puzzles are already solved. How it is as a result of that neutrino oscillation. That means I'm not going in detail about experimental, but that is super Kamiokande detector, which is constructed in Japan. They have used that heavy water, and the design was for detection of atmospheric neutrino. And these neutrino interact with the atomic nuclei in water to produce electron, muon, and tau leptons. These atmospheric neutrons are mostly muon type neutrino. So this super Kamiokande collaboration discovered that muon neutron converted or oscillated to tau neutron when they pass through the earth. This oscillation or this conversion or this transformation of a muon type neutrino to tau type neutron is known as neutron oscillation. And these neutrino oscillate in flavor because they have mass. So in order to exist the neutrino oscillation, neutrino should have mass. However tiny it may be, it should have some mass. Now in 1998, this super Kamiokande collaboration announced the first evidence for neutrino mass. Okay. Now this super Kamiokande was also used to study solar neutrino. And it is found that the fusion reaction that takes place in the sun only produce electron neutrino, but the neutrinos which are consequently oscillate into both muon and tau type neutron, what are produced at the surface of a sun, and what we are detecting at the earth, it is found 1/3 of the neutrino, and 2/3 of the neutrino we are not getting electron type neutrino. Why? Now it is found that these on the way, while they are coming from the sun to the earth, they are transforming to muon type neutrino and tau type neutrino. So meanwhile, at that time, that Sudbury Neutrino Observatory SNO was constructed in Canada, and it was designed to detect this solar neutrino. That SNO could identify the electron neutrino because it is filled with heavy water which contains hydrogen nuclei with an extra neutron. The combined data from Super Kamiokande and SNO determined how many neutrino, that means muon type neutrino and tau type neutrino, were incident at the detector. So both the Super Kamiokande detector as well as that SNO, they are able to detect how many of them are muon type neutrino, how many of them are the tau type neutrino. So the problem which was initially electron type neutron was produced. We are detecting 1/3 of the neutron as electron type neutron, but 2/3 were that muon type neutron and tau type neutron. So the SNO results also provided further evidence for the neutrino mass and confirmed that total number of neutrino from the sun agreed with the theoretical calculation. That is why Professor Kajita and who was the leader of the Super Kamiokande, and Professor McDonald, which was the director of SNO, received the Nobel Prize for 2015 for the discovery of. This was actually what happened. Actually, if you consider about mathematical equations, then rigorous quantum field theoretical calculations are required. But I am not going in detail about those things. But I, with another professor, Manasi Goswami, who is working as a professor in Regional Institute of Education, NCRT, Bhubaneswar, Odisha, we tried to explain this phenomena. Why neutrino must have mass? To the school children, to the high school children. How we will explain that neutrino has some mass? For that one, we have used simple equations, two equations. With the help of two equations, it is published in Science Reporter, popular magazine. I think our students, almost all the students know this magazine, which is published in 2008. We have considered the simple equation that mass energy relation, that mass with that of the speed, E equal to m0 c square divided by square root of 1 minus v square by c square. So using that equation, we can explain for the case of massless particle, we can write E by gamma equal to m0 c square, where m0 is the rest mass of the particle or inertial mass. If m0 equal to 0, then E by gamma will be 0. If E by gamma equal to 0, since energy is generally non-zero. This implies 1 by gamma is 0. 1 by gamma means square root of 1 minus b square by c square. So if this equal to 0, then we can say that v equal to c. That means only massless particle can move with the velocity that of the velocity of light. Thus we conclude from the above discussion the particles of a zero mass exist only at the speed c. That already we have read about from that special theory of relativity. On the other hand, we can say that if a particle has some mass, finite mass, then they must travel with a speed which is less than the speed of a velocity of light in vacuum. C is the velocity of light in vacuum. Then we consider another equation, mass time. Delta Tm equal to delta Ts divided by square root of. I think our students who are present here, they are acquainted with this equation. And this gamma into delta Ts, where delta Ts is the proper time. That means the time interval on clock at rest and or stationary relative to an observer. And delta Tm is the time interval on the clock in motion relative to the observer. So, and gamma is always greater than 1. We can say that gamma is greater than 1. So now, for a massless particle, if we consider the photon, the rest mass is 0. Already we have seen that for rest mass, when the particle mass is 0, it travels with the speed, which it travels with the speed of light, that is c. If v equal to c, then gamma will be infinity. So if gamma equal to infinity, however tiny it may be, this will be infinity. Delta Tm will be infinity. What is the meaning of a delta Tm infinity? So the time dilation equation for any finite interval delta Ts, delta Tm will be infinity. If delta Tm, what is that? Is delta Tm, what is the physical significance or physical meaning of this equation? That means if this means someone at rest on earth watching the photon fly, by will see it is an internal clock. Clock attached to the photon take infinitely long between ticks and talks. That means we can say that he sees the photon's time passes infinitely slow, as if the time stops for the photons, or we can say that photons are timeless. What is the again also what is the physical meaning of this timeless? That means they can travel for billions of years without the passage of any corresponding proper time. That means there will be no change, which implies that for a free photon, we can say that a free photon cannot undergo spontaneous change. That means photons are changeless. When we are considering photons are massless, we have shown that it is timeless and also it is changeless. So we can give the conclusion that photons are changeless as well as massless. Sorry, photons are changeless as well as timeless if photons have no mass. Now you come to our point that neutrino. If neutrino is massless, it moves with velocity c, then it must be timeless as well as changeless. Changeless means it cannot spontaneously transform from one form to other form. That means it certainly cannot oscillate. But already neutrino oscillation is well established, for which Nobel Prize is given. So we can say that what we have assumed, that neutrino is massless. That is why we have reached at the contradiction. It cannot oscillate. But already it is seen that it is oscillating. That is why what we have assumed, that neutrino is massless, is wrong. That means neutrino has some mass. However tiny it may be, it has some mass. So, but it is observed that neutrino undergo Flevel oscillation, which implies neutrino must have mass. So this is our explanation to explain the neutrino oscillation to school children. Then what is the utility of this massive neutrino? This massive neutrino may be one of the candidates for dark matter. Till now, what is the particle theory about the dark matter and what are the proposed? There are many proposed candidates for dark matter, but there is no conclusively candidate for the dark matter, because so far what are the different dark matter candidates, they are not satisfying all the properties of dark matter. So one of them is that neutrino, this massive neutrino can be considered as the candidate for dark matter. Again, this is small neutrino mass. Already we know that in the standard model neutrinos are massless. If neutrinos are massive, then it will go beyond the standard model. So it will give new physics at the scale ranging from TeV to grand unification and superstring scales. The very smallness of a neutron mass leads to many theorists to believe that they open a new window on the physics much higher than our accelerator can reach. And these neutrinos are important for the study of a sun, stars, core collapse, supernova, origin of a cosmic ray, etc., etc. Now, these tiny neutron masses are great interest because they might arise from some fundamentally different mechanism to the way the masses of other particles that generated a Higgs mechanism. Although standard model is very successful to explain many low as well as high energy phenomena in particles, but within the framework of this model, it is not possible to realize the massive neutron. That is why I said the existence of massive neutron is not explained in the standard model. That was I have explained as one of the limitations of a standard model of particle physics. So the existence of a neutron mass is one of the signature of a new physics beyond the standard model. Then some outstanding mysteries about the neutrino. How do neutrino gain mass? Already I have said about the Higgs boson. Higgs boson is providing mass to every fundamental particles, but it is found that the origin of a neutrino mass is not explained with the help of a Higgs boson. So there are some different phenomena like seesaw mechanism. It is proposed, but not till now it is not well established, or we are not getting the satisfactory answer from where neutrino is getting mass, or what is the origin of a neutrino mass. Then what are the absolute masses of a neutrino? Although the values of a neutrino mass square differences are known, that means m1 square minus m2 square, that is delta m square, is detected in some experiments, but the absolute mass of the neutrinos are not known so far. Again, the fundamental nature of a neutrinos, Majorana or Dirac. Majorana are a particle, is a particle whose antiparticle is same with that of the particle. So our neutrino is whether it is a Majorana particle or a Dirac particle. Dirac particle has different antiparticle. For example, Dirac particle is electron, its antiparticle is positron. But Majorana particle is that which antiparticle is itself. So whether the neutrino is a Majorana particle or Dirac particle, it is not known confirmly. It is expected that neutrino less double beta decay. Already I said one term about beta decay. When a neutron decays into proton plus electron type neutrino, anti-electron. But when we are considering two protons decay into two neutrons decay into two protons, two neutron, two proton plus one electron and anti-electron, neutrino. That neutrino means one will be neutrino, another will be its anti-neutrino. This neutrino and anti-neutrino will convert it into energy. So at that time we will get neutrino less double beta decay. The experiment is going on, but conclusively we are not getting the result about neutrino double beta decay. Are there more neutrino? I said there are only three types of neutrino: electron type neutrino, muon type neutrino, tau type neutrino. But nowadays, some scientists, they are proposing another type of neutrino, which is known as sterile neutrino, but it is not conclusively. He said that this is the fourth type of neutrino, because actually what we are saying that a neutrino, these neutrinos possess weak nuclear hypercharge, that is, but no electric or color charge. But this sterile neutrino has no weak nuclear charge or hypercharge, as well as that of the electric charge or a color charge. That is why it is inert particle. We are saying sterile neutrinos are inert. Why are neutrinos light and neutral? Can we observe CP violation in the leptonic sector? These are the unanswered problems in high energy physics now. If the students who are present in future, if they will continue their research in this direction, they may give the answer of these queries. The aim of these current and future experiments are to study the neutrino oscillation, search for neutronless double beta decay, measurement of absolute neutrino mass, and the nature of a neutrino, whether they are measured or Dirac particles. And the neutrinos have and will continue to provide important information on structure formation in the early universe, Earth, solar, and supernova physics, nuclear properties, etc. The study of neutrino physics and implications results connects many disciplines like from particle physics to nuclear physics and astrophysics to cosmology. We have no doubt that an exciting future is ahead of us. Thank you all.
Thank you very much, sir, for your highly excellent and informative talk. We are very much thankful to you for your valuable time and to enrich the knowledge of our students. Actually, you talked on many interesting phenomena in high energy physics. You talk on string theory, which is the theory of everything, and especially the concept of six dimension, because till now the students are aware about the four dimensions. Now we talk about six dimension, and the concept of invisible universe, which is about 95% of the universe, and finally the neutrino oscillations. All are very informative to our students. Now the session is open for any questions or queries. If anybody has any question, they can ask to our speaker. So if anybody has any questions, they can ask now. I think there is no question. So we thank to all the participants for their patience hearing. And once again, I thank to our speaker for his valuable time to enrich the knowledge. Thank you.
Thank you all. Thank you, Dr. Rajesh Kumar Agrawala.
Thank you very much. And till now we have come to the end of the session. Thank you. We can leave now.
হয়ে গেছে? এন্ড করে দেবো?